I was thinking of making a battery dispenser, and I was inspired by one that Chuck Hellebuck recommended on his YouTube channel, CHEP, and that is a model available on Thingiverse, and that model does include SketchUp source files, I believe. Yes, but SketchUp is not a program that I use, and I wanted to make a parametric model. I prefer to use free software, that is software that you are free to use, to share, to improve, and in particular to keep. Because one of the problems I have found with proprietary software is that the companies tend to decide that you are going to use the new version, and no matter if the new version actually works properly or for you or not. And that's if they stay around, because they will frequently just drop the software that you're using and make another one, or just close the company entirely. So I may have guests on Geek Streams. So I have already started a design, and this version is, well, largely working, but it suffers from a few problems, like there is no easy way to switch between what sort of batteries. And well, if I change the capacity here to say 3 shelves instead of 6, we'll see that it doesn't actually adapt correctly. So there are corner cases it doesn't adapt at all, because it has already broken. So I wanted to rebuild it, and that is where this stream comes in. So I make, well, I think I shall start pretty much from scratch. I mean, this is not of interest. This table won't help us, but this table does contain some parameters that we will want to keep. These are different sorts of cells, frequently termed batteries, that we might want to put in our battery holder. Now, for starters, there are no labels in this sheet, and FreeCAD's handling of labels is a bit inconvenient, to say the least. FreeCAD does not come with an easy way to move the labels between cells, and you have to select an individual cell and apply the alias in the cell properties dialog. Now, granted, when you are in the spreadsheet workbench, there is a shortcut to the particular tab, but it's still opening a modal dialog box for every single cell, and it's a pain. So this has been noted by a lot of people, and therefore, if we check in the add-on manager, there are macros available that make this a little bit better. In particular, there is this alias manager. You can follow the link to the wiki, and from there to the forum thread, and other people have made improvements to this, but I'll start with this version for now. So we install this macro. Now, keep in mind, this macro is just a convenience, and it hasn't showed up anywhere in our user interface, so I will also add it to the user interface, so to demonstrate how that is done. As you can see here, we have the alias manager is now available as a macro, and we can set it up as a custom macro here. So we can assign spreadsheet cell aliases is a decent name in a menu for that. Let's also select an icon. I think that the label icon that is used for the first shortcut will do fine. And sometimes things are a bit slow in this case because it's got a lot of icons to dig through. We want the spreadsheet icon for labels. It should be around here. Right there, in fact. So we add this to our custom macros, and we can also set up a hotkey there. Then I go to toolbars, and I now find the macro under available options, but there is no custom toolbar in the spreadsheet workbench. So we add one, and it's just custom one, which is a terrible name, but it doesn't really matter because this name is not displayed. And now we can put this in and we get another toolbar with our macro. That makes it much easier to access this macro. A particular limitation of this macro is that it only works on the very first spreadsheet created within one document. Because I'm going to calculate some parameters based on existing values, I will hang on just a moment. I should guide someone to my actual YouTube stream if I can find how that is done. This should be the stream, and copy link address. So we have the battery holder that I wanted to design is in this battery holder document, and I have started a new document that is called unnamed. So we're going to design a spreadsheet for use with this alias manager macro that I found in the add-on manager. Let's start with the first spreadsheet here. We need to activate the correct document. There. So with this label add-on, the first column is going to be the names of all of our parameters. So we have cell types, for instance, and we have for each cell there is a diameter and length, and we will be targeting some of the various parameters for the holder itself, like a layer height, because I am designing for FDM, that's ordinary plastic extrusion 3D printing. And in that construction process, everything is actually printed as horizontal layers typically, so I want to calculate slopes such that the batteries will still roll. We'll have a bit of a margin just to make things move. We'll have wall thickness. We'll have cells available to pick up at the exit, and we'll have capacity per shelf, and we'll have a count of shelves. So this basic design, there is an exterior part, which is this exit cells value. There are shelves in here. I'm counting the bottom floor and this shelf back and this shelf. So this would, in my model, be a 3-shelf design. And apparently they have only room for about 3 cells. So in the comparison, that would be 3 by 3. So let's fill these parameters in. The top row is intended for names for various parameterizations of the model. So you can make a range like having AAA and AA holders that are roughly the same size using this alias manager. That is what the generate part family is designed for. It allows you to build separate documents from this master template that have each of the different parameters saved or active. So we are going to use AA, and we are going those have a diameter of 14.5 millimeters. They have a length of 50.5 millimeters. And it is a good thing that units are supported within the spreadsheet. This reduces the risk that you pick up a parameter for some other field if it's not dimensionally compatible. Our layer height, I will probably be printing this pretty fast, so 0.28 millimeters or some such. 3D printers have various parameters, and this may be one of the layer heights I use, but for the moment it doesn't really matter. Let's enter the other cell formats as well, and then we can close the original document that well, is broken, but I used it to figure out a few of the possible methods to build this construction. So the AAA, that's 10.5 millimeters, and length 44.5 millimeters. The A cells, what are even A cells? I don't know. I have them in the table for some reason. Diameters. So this is just simple data entry. We will be getting to more interesting stuff eventually. C cells and D cells may actually be of relevance here. Of course, a bunch of these parameters maybe shouldn't be varied, like wall thickness and layer height, but for the moment I'll just have all of these columns, and I may tune them later. In fact, one of the parameters that is a bit dubious which way to go is the number of shelves and the cells per shelf, because it may be more interesting to design them for a particular size than a particular capacity. And speaking of that, let's actually enter the capacity here. So the capacity will be in oh, so let me just finish with these. And 61.5 millimeters. So I will be using a margin of 1 millimeter. This may be a field that you want to split in more categories, because there's margin at the ends and margin around the cell, and I'm going to use it for pretty much how much wider I make all the channels where the batteries need to pass. The wall thickness I'll leave at 1 millimeter as well. The exit cells, I'll use 2 cells at the exit, and it was 3 and 3 per this. Oh, right. So AA333 should have 333. Here comes the use of this label manager. I can set labels on column B, and I want them down to row 10. And the script completely failed. That is not actually what I expected of it. I will make one attempt in particular to see if I can get a version of the script that works better. Like I said, there are links we can follow. So add-on manager, this macro has a link here, and this link goes to the forum. And in the forum, if I check, well, not that one, that's my ugly script, can do a similar thing, but not quite as much or as elegant. But here is a version contributed by Howell, and if I just edit this macro, replace all of its contents with his version, and try again, B2 to 10. No alias found, resetting, unable to complete task, unable to complete task. I do believe something in this script is having a problem. I'll try restarting FreeCAD. First saving this document. And see if it gets less confused. If not, I guess I will use my script for the moment, because using that add-on is merely a bonus. So let's open this spreadsheet, and see if I switch to the spreadsheet workbench. I still have my button, and if I run it, it says found no alias entries, no alias found, resetting, unable to complete task, unable to complete task. I don't know why it says that. One possibility is that all of these should be in a single word format, so they work as symbols. Now, there, set aliases, B2 to 10, aliases set, and they have turned yellow. You can see with the tooltip that they are set to the names that are in this column. I think that having the spaces in there, which makes them invalid names for the aliases, caused the script to fail, but I'm not entirely certain. Interestingly, it has not set cell type. So, well, who knows? Doesn't really matter. What does matter is that now that these parameters have their names and are therefore exported in this combo view under data for the spreadsheet object. We can also rename our spreadsheet, but this is the source for all properties we're going to use in this design. So next I want to calculate a few of the properties that follow from this particular parameterization. For instance, the capacity is very easy to calculate. It's going to be exit cells plus cells per shelf cells per shelf times number of shelves. So it's apparently down arrow to use that completion. 12 cells is a fairly small capacity thing, so I'm likely to make a larger version myself. But that's for later. We will figure out, we can place some parameters here that are just informational, but one of the weaknesses of FreeCAD is that when connecting data fields like these, a spreadsheet is regarded as a single unit, so any update to the spreadsheet will cause anything that depends on that spreadsheet to update, and vice versa. This means that if I have a separate sketch, for instance, calculating the distance between shelves, and I use that combined with the number of shelves to calculate the height, then we simply will not get that data should not go into this spreadsheet. I should use another spreadsheet for that information. You can also see here that parameters is actually the label for the spreadsheet object. The name is still spreadsheet. And that's important for this add-on, because this add-on only operates on the object named spreadsheet. That's why it doesn't work on another spreadsheet. Like if I create another spreadsheet, it's actually named spreadsheet 001. And I'm going to use a second spreadsheet, so that's when all of this matters. This spreadsheet is used as my plan is to use it to collect some shortcuts to various things that I calculate graphically. Well, really it's calculated numerically by the FreeCAD equation solver that is part of the sketch system. Let's call this consequences for the moment. Consequences that I will be interested in will be, for instance, the shelf angle and the container depth, as well as now these are slightly tricky to calculate, so I will want them as distinct parameters that are easily accessible. And now I'm wondering why this cell is yellow and this cell is not. Have I lost one of the aliases? Wrong button. Yep. And this one is correct. So I have no idea how that happened. Clear aliases and set aliases, and now they are all marked. Apparently I'm going to want to fix this script at some point, but that's for another time. So, time to actually start designing things. I am going to use the Sketcher, and the Sketcher is the same tool that you use to design sketches inside of part design, but in this case I am making some standalone sketches. As you can see here, it's not inside any part or body, because I want to use them to draw some of the properties. For instance, we have discussed the shelf angle. This angle is chosen such that a cell will roll. So we design a cell here. It is of some size. This size, I'll have a constraint, and this is when I use a formula here. The equals key works fine just to start entering formula. For some reason, if you hit equals again, you get an invalid expression, so that's not terribly helpful. But we can use this to get properties from parameters. In this case, we want the diameter parameter, but we are setting a radius here, so we divide it by 2. That is how large a AA cell is. And we want to design the shelf. Actually, it's time to insert another row here. I want the roll margin, which will be much smaller than the ordinary margin. This will be how far into the cell I will place my limit. We will see what that means soon. The thing is, we want to make sure that this cell will roll off of this corner. This is the layer that is directly below. And let's place a bit of a limitation on that too. So the layer height here. So this is the layer that is directly below the battery, this particular cell, and we constrain them together, and we see that this cell is teetering just on the edge of this layer. Now that's not so bad in itself. Obviously much of the sketch is not completely constrained, and doesn't really matter much. But if I were to draw the next layer here, clearly this next layer won't be quite this size, but the next layer will be the same height. For this cell to continue rolling, or to start rolling, we want this to be inside this circle. Because if it's inside this circle, then it means that this cell has not been able to land on this corner right here. That means this is not actually the position that the cell will ever be in, but if this point is also aligned to this cell's wall, the circle, then it can stop. Just barely, but we want to have a slight margin, something that tells us that it doesn't stop. So we do this by adding a point. We say that this point is not only on the circle, it is also on this. And here, this will be our rolling margin. I have not yet set that label. So let's set that label. I'll do it manually this time. So this is the way that you can set labels if you don't have that script. It works fine. It's just tedious to do when you have a dozen of labels to set, particularly if you have a dozen of labels to move, because you have to remove them first so you can set them somewhere else. And in the meantime, things will be invalid that are depending on them. So this was to be the roll margin, and with that we see that there is now an overlap. This corner, we also see that the circle is not actually a circle, it's a bunch of segments, but the numerical solution still exists. There is a weakness in this construction, and that is that if we were to change the parameters, these 2 points may not stay the same relative to each other. It could actually flip them, like in this case the diameter is 14.5 millimeters. If I were to change the diameter to something much smaller, like say 2 millimeters or 3 millimeters, it will only pull the point that is constrained to be on that. Actually, it didn't. Why did it not update? There. Now it's updated. It will only pull this point. Luckily, it seems that this did not, in fact, invert our directions. So let's see, it was 14.5 millimeters, right? You can actually see in our complete history here what it really was. I filled it in at some point, but it doesn't matter. What there we have that. We still have this constraint going to the right as it should. So using this knowledge, we can construct a line along which these points can be. This line, let's just make this line really, really long to illustrate what it's doing. So by placing this corner on that line, and that's actually the wrong one, I want this corner specifically on that line. Now this line is pointing off somewhere at a very specific angle. This angle will keep this battery rolling, even though there are these stair steps from the layer height. So that is the reason that I designed the layer height into these calculations. And knowing this, I can take the x-axis and this, and I can place an angular constraint on it. It says 8.4 degrees. Now it says it cannot set this constraint because it conflicts. we already have enough information to calculate this angle. So I toggle this between constraints and reference mode. As you can see, it's now blue. This means I now have a reference value. This value will show up in blue among my constraints. And I can rename it to shelf angle. And here comes the reason that I wanted to have this secondary spreadsheet, because now I do have the shelf angle value under these constraints. So it is accessible, but it's only accessible by going through this sketch. I'll call it shelf angle solver. By also placing it inside this spreadsheet, I make it easier to manage all of the constraints for other parts. So I will use the, as you can see here, on S, shelf angle solver that I just renamed my sketch to is not available. It's still called sketch. And this is one of the reasons I don't want to keep typing these in different places, because sketch, sketch001, etc. is not very helpful for locating things, particularly if the sketches have since been hidden because they are part of some part. This sketch is purely a construction reference, so I will be keeping it hidden most of the time, and I will not be extruding it or making any holes with it or anything like that. So the value is inside of the constraints. So the formula is sketch.constraints.shelfAngle, and it is now also inside of this spreadsheet, and I can set the alias for this cell there and make it much easier to refer to things, because consequences here it's just one thing to keep track of. It's spreadsheet 001, but I believe that we can also access it by the name of consequences. In fact, that's exactly what we did with parameters. So if we check this constraint, we see that shelf angle, well, all of these unnamed constraints here, we can actually name them if we want to make it clear what they mean. All of them refer to parameters label. So we don't need to use the spreadsheet or spreadsheet 001 name. We can use the names parameters and consequences. We cannot use shelf angle solver, which I believe is actually, again, because I have written distinct words. So if I write this, we see the little blue check mark here. That indicates that consequences is dependent on this object, and it is still blue, so the constraint should still work because it refers to sketch. Oh, ignore the game update, it doesn't matter. But now that it is a valid symbol, we can use the name shelf angle solver. So if we are careful to always name our objects such that they form one word as far as FreeCAD symbols are concerned, the limitations are a little bit more distinct than that. I think it's something like C symbols. So uppercase and lowercase letters A through the Z. Digits and underscores are allowed, but not as the first character. Anyhow, we can use these names, but I find it easier to just have these two parameters and consequences to refer to. So we can make another sketch. Can't map the sketch to selected object. Well, I don't need a selected object, I just need a sketch. If we draw another sketch, and we may want to remap these, it doesn't really matter now because I'm not drawing things in them. I'm going to figure out a few more things about the dimensions of our storage. One of the things is that we have an exit shelf of some sort, and we have here a number of cells that are in a row. So we form a line from this one to this one. We place this on the line as well. We say that all of these circles are of equal size. What I'm trying to figure out right now is how large the container will be to fit the given number of cells. We have a number of exit cells and we have a number of cells per shelf. Actually, we'll add one more of these and mark it as equal size. So we now have cells at either end of this line. This line, in fact, I will mark it as a construction line because it's not a physical part, but when these cells are rolling along, these are in fact touching, and I can tell it so by adding a point, and this point will be on this line, and it will also be on this circle. And of course, our first external constraint here, we want to set the size of these. Again, to parameters, diameter over 2. Obviously we could have the radius written somewhere in our system, but now we have a distance between these two. This distance should be that diameter times, let's see, if there's only one cell, parameters.exit cells. If there's only one cell, then these two circles will be the same. So we subtract 1. And we place this point on the horizontal axis, and all of a sudden I have messed things up because I can't access my second circle anymore. But it's there somewhere. and it may be easier to drag this closer. So that's one of the inversion problems that you may see at various points. One of the solutions here is to constrain this distance as well, but this I think is an over constraint. Well, it's technically an over constraint, but the solver doesn't seem to mind. And we place that point there. So now we can't drag these cells around anymore. And this will be the last cell that's inside of our system. So our storage, our main storage will be something like this. Let's just, we actually have some sort of redundant constraint here. I don't know what it is exactly. Constraint number 13. Yeah, so it is this one. As I suspected, it can deduce this because we have specified that these two circles are touching at this point and they have this line going through them, so this point is at the largest distance and this matches their radius. So this constraint is redundant, but I can also remove, let's see, if I say that these two are of equal size, then we are no longer over constraining our system. So this line will be at the angle that we calculated earlier. So let's set that. It is consequences shelf angle 8.4 degrees. Now those cells can change size now. That is not what I intended, but that is because we have removed the constraint here. There you go. So our system is far more constrained at this point, and we have this constraint for the external cells. We see that there's room for 3 of them, and we write a similar constraint for this distance. And it's again parameters dot cells per shelf -1, all of it parenthesized, and multiplied by the diameter. Finally, we will want this this wall to have a bit of margin, I believe, because this is how many cells would fit if the shelves were perfectly straight. They won't be, but we will find that a little bit later. For now, we have quite a few constraints in this system. The expanding battery is a cool idea. Well, it's not the battery that expands. The idea here, or did you just mean the glitch? I'm getting some comment on IRC, so apparently I have at least one person watching. That's fun. Now, I'm going to design in a shelf. The basic idea is that this shelf will support the row of cells. So obviously it needs to be parallel to this line. But the challenge at this point is figuring out at what height this will be. So I'm going to add another construction line here and say that this point is going to be, say, directly below this, and these shall touch. And actually no, I'm going to add an arc. This arc does exist in the final design. This point to somewhere around here. Now this arc is not terribly visible, and we have a bit of a corner here. I don't want that corner, I want this to be a perfect join. So this will be where this cell stops. This is the end of this shelf. And let's just move that constraint out of the way. There is a point here. Well, it doesn't actually matter if this point is on the circle or on that arc, but I'm going to use that arc, and in this case I selected the arc among the elements because it overlaps perfectly with this circle. I can't be certain to select it. So this point is on there, and it's going to be vertical with this center point, so that's directly below the cell. That means that from that point to the floor I am going to have the wall thickness. That is how thin my shelf gets at its thinnest. So we get that again from parameters, wall thickness. And now this shelf doesn't move around anymore. We are not hovering in the air. This gives us a few more parameters that are of interest. Because now we know how high along every point on the shelf that this surface will be. We find out where the floor is. And I need this in some form to figure out how high the shelf where the shelves start, because I'll have a later step to find out how far apart the shelves are. So this is a rough and basic design. We don't know where the shelf ends right now. That will be based on where this cell rests. But if we take a look at the Thingiverse thing again, we can see this stop wall is much the same, and we now have this angle. We have how high this box will be compared to this shelf. We can actually start drawing in some of these walls just for informational purposes. Like There's a wall here and a wall here. But there's one interesting thing that I've no idea what bat RW is supposed to mean. By the way, I do hope that you are hearing what I say and that the audio level is reasonable. We see that the back walls here are rounded a little bit. So that's the next detail that I'm going to tackle. And when doing that, I'm going for convenience to use, I'm going to use a circular arc. And obviously the shelf will end at some point and the circular arc will go up, and I don't want these to have a corner, so I use T, and FreeCAD switches it to a endpoint to endpoint tangency and removes the coincident constraint. That's just FreeCAD actually being helpful instead of failing something. And we touch this wall as well. Now, what should the radius for this be? As you can see, I can move this point around quite a bit. If the radius is smaller than the battery, then we see that the battery will never actually contact this curved section. So we don't want it to be smaller than the battery. If it matches the battery exactly, then the battery will strike that entire surface at once. And furthermore, that would mean that at the bottom of this curve is, well, since it matches the angle here, it would still start rolling. But there's an additional complication in that there will be another battery on top. This battery is the same size as this one. We need to select exactly the right things, and this touches. So when designing this, we want to be sure that the battery from the shelf above does not strike it on the left side such that it keeps this battery in place. We want it to fall on the right side or straight above, because this battery must be able to roll even though this battery is laying atop it. So that's one of the funny parameters that I'm not entirely sure. I am not going to engineer that with precision. However, I have made a choice for how large to make this. I am going to simply let this point be the lowest point of the shelf, and that means that this entire radius should be the channel width. That is not only the diameter of the batteries, but also our margin. So I choose to set the radius of this to parameters.diameter plus parameters dot not roll margin, this time the main margin. And we're going to place this point where this cell is. Now it is constrained, and we see that this battery will be way out over here. Because we know that this point is actually somewhere, that is actually where the shelf ends, we can see that this battery on top must be to the right of this battery. at least for this position. If this support battery is not actually doing anything right now, so let me remove it and add 2 more things. Oh yes, we have one more parameter, or a couple more parameters to think of. We are going to introduce an overhang angle. The overhang angle, when 3D printing, is the shape, is how far out you will allow your walls to lean. Because if they lean too far, there will be nothing to support them, and we will need to add additional supports to print the shape. This design is built to print without support, and that is why you see these angles, for instance. And in particular, that is why this shelf gets narrower as it goes along. And this is quite the desirable feature. The same thing, we can see that the actual profile at the end of the shelf is triangular. It may be a bit hard to see in these pictures, but if we open up this model viewer, then hopefully it is possible to see there. This triangle has particular properties because the angle at which this is leaning out of this wall, that is the overhang angle for that overhang. And that's the same thing down here. And in this model, the only overhangs are under these shelves. So since we've been working on the bottom shelf, we haven't encountered any overhangs before this. But now I want to make the second shelf. Or at least I want to find out a few parameters about the second shelf. And this is when I am going to just design things that aren't in this plane, really. Conflicting constraints, where are those? Have I made some sort of mistake again? We have a conflict. Constraint number 55. If I turn it, that constraint is, we'll remove that constraint for now. I think that what it may have been saying is that this cell is actually touching this curve and not this line, so it was constrained to the wrong part, and that's a very finely tuned thing, so I think we can get away with faking it at this point. The important thing is that this point, which will be the lowest point of our upper shelf, has some space from this cell. And in fact we can measure this. Again, we switch to reference mode and we take the distance. Actually we take the distance from there to there, and we see that this distance is 8.25 millimeters. And 7.25 millimeters is the radius of the cell. So 8.25 means we have 1 millimeter margin, and that is exactly as planned. So I am going to draw a couple of cells more. All cells are the same size, equal, and these two shall be touching, tangent. And I'm going to use these just to experiment with what happens when things are rolling through here. So the upper one will be rolling along this shelf. I'm going to make that vertical as well. And this is when things get a little dicey. We see that this is still possible to move. I need another constraint. I want this point and this wall to have a particular distance. This I actually don't want to be a reference, I want it to be a real constraint. Parameters dot diameter plus parameters dot margin. This makes sure that oh, I'm still missing something. This makes sure there is enough room for one cell to drop from this shelf onto this curve. So since this constraint is the same as this constraint, it tells us essentially that these two are at the same vertical position. But we have at some point lost our constraint that tells us how long this space needs to be. Also, I want to make these a little bit more sane, so these two I can actually remove this line, I don't need it, and I want this to be the same point. Redundant constraints. Number 62. Ah, yes. So that constraint was actually completely pointless because I already said that this curve is tangent to that wall. It didn't add any information. What we want is for this battery to fit, but to still be in this space. The overhang angle, I don't know what I will set it to, but we will start with 30 degrees. And that angle should be this angle. And this triangle is based on the triangle here. So it's actually pointing outwards of the plane of this sketch, but I'm using it to calculate sizes, so I'm okay with that. And we add another parameter here, insert row, and this should be minimum shelf width. Let's make that 3 millimeters. I copy that and properties, alias, paste, and we're done. The point of this is we now get how high this shelf is by using that triangle. And I'm going to use these to estimate things. Now, if this touches then this battery is moving along this outer circle. Now, things are moving way too much here. So I think that I shall place this point on this cell for the moment. Doing that means there is room for more cells than we actually need. But the point here is that with the next cell somewhere up here, we are going to have actually this should not be a construction line. There, and I'll make this not a construction line as well. So this will be the surface of the next shelf. We do that by setting its angle again. Easier if I select the right constraint. And that was from the consequences shelf angle. Okay. So now we see that although these two lines have the same sort of constraint, they are not parallel. And in fact, they should not be. So this shelf will have yet another arc. It will go from there to there. This should be tangent, and this should be tangent, and this should be as large as this. So now we see a rough outline of the two shelves. In fact, this I don't want it to be a construction line there. And for the proportions, we are going to constrain these to equal, and we are also going to set them to the wall thickness. There. We also want this point to allow that is passed. So we shall place another construction line. This construction line goes from here to here. We make this normal, that's n, such that it describes this opening. And now I can constrain the length of this line to, again, diameter plus margin. Now, if I was thinking ahead a little bit more, then I would probably have stored this value as something like, say, tunnel width. That would make a sensible parameter. If I did, then I would want it to be in this first spreadsheet and not in the second. And the reason is that I don't want these solver sketches to depend on anything in the second spreadsheet. With that in mind, I actually have a problem already. All of the sketches that are depending on this shelf angle. So the idea with this is to see what actually happens as things roll. We can see that first we have assumed that this cell drops straight down at this point. That's not entirely accurate. The first point that is accurate is here. And this is good enough. We are still looking at this battery touching here. It's got more distance to fall, and this is still supported by the shelf, so it should not be applying too much pressure. It's not until we get here that this cell is really pushing on the left side of the next cell. But as we can see, it's almost entirely on top of it, and there is no harsh angle below it, so it should roll just fine all the way to here, which is the flipping point where the two cells are vertical. After that, it's no longer a problem that this battery is turning clockwise, and this battery needs to be turning anti-clockwise. And at different rates. So I think this geometry will function just fine. We can also see that we have from this point, the opening, to this point, that will be the bottom of our shelf. Whoops. So that means we have in fact designed the entire outline of a shelf in this sketch. Quite the accomplishment. But this is the outline of the shelf as it appears exactly at the wall, so back here. We're going to need to cut away some portion of it in order to guarantee that overhang angle. Anyway, that's a bit of a start, and I will be taking a break, I think, and then we will continue designing the outside lip and separating the shelf into a different block. And once we have this shelf as a different block, we can make an array of it for how many will be going up, and make a mirrored version for the shelves on the other side. But this, I think, is a halfway reasonable start. And we have an under-constrained sketch with 4 degrees of freedom. This represents at least 3 of those degrees of freedom. So this is the 4th degree of freedom. I don't think I care much about that right now, but we can at least define one of them. That's because we know how many shelves we need, and we will now know how far apart they are. This is going to be a little bit tricky, but it's possible. You see, there is a point somewhere on this surface that has the same meaning as this point. And so it's going to be the same distance here, and that distance is the same as this distance. So we can take this point and this front wall and apply. Actually, we can't select the wall because it's just a special case that you can do that to axis for some reason. This distance should be the diameter plus the margin. And again, I'm almost always using diameter plus margin. But that means this point and this point are at the same place on their respective shelves. And that means we can now design the shelf height. So we make a reference constraint from this point to this point. Vertical. And this is one of those really odd numbers that I would not want to be solving for manually. And this constraint I wish to rename to shelf height. And at this point I think that I can define the distance from this to this. This is one of the odd points. I will want to add a line. From here to here. That line has a redundant constraint. It's saying that it's vertical. It's already on a vertical line. But I want that line right here. Well, I was about to use vertical constraints now. It doesn't really matter. The exact height of this, I want to base it off how many shelves there are. So I want it from this top point to here. I want a vertical constraint. This constraint is actually a real constraint, and it should be constraints.shelf height times parameters dot shelves -1. Reference constraint from this sketch cannot be used in this expression. Right, let's just set it to 50 millimeters for now and calculate the height in a separate step. Right now this just constrains our sketch a little bit. These two were just used to examine the parameters, and we don't need them anymore. And we have 1 degree of freedom in our sketch. Where is that degree of freedom? I am actually far from certain, because this triangle is constrained. Now I have an idea. It's this. Remember what this point is? It's the end point of an arc that resembles this bottom wall that catches the last cell. So in order to make it, I'm going to, let's see, I'm going to add a line that goes horizontally out of there, and I'm going to constrain the angle between these two. Apparently I can't do that. I'm just going to make it so that this point is a little bit above this point. Let's call it 0.5 millimeter. And the entire sketch went green. So that curve, where it ends, is not actually all that critical. It's going to end slightly above here because I want to be sure that as the battery comes rolling, it doesn't jump out of the dispenser. I want it to be heading to the right if it is rolling off that lip. That comes when I actually make this shelf, and I might be turning this sketch, well, this sketch contains critical geometry for several different parts that we are going to make different parts of. There is the shelf here, complete shelf outline. There is the bottom shelf here, and there is the container size itself. We actually have the container depth here. The container depth is from here to here. So we make a reference constraint. We name it. There are other shortcuts for naming a constraint. But if you double click the constraint, then it seems that you turn it into a full constraint, and a reference constraint should not have a value set. It should read the value. So we name that container depth, and we are now for the moment done with this sketch. I'll call it shelf size sketch for the moment, and I will set the label on this cell. And I will set it to a value as well. Well, that's odd. Oh yes, back to the problem. We cannot refer to things in this sketch in this spreadsheet. So we're going to need to use either back references to this sketch inside of this sketch, or another layer of the spreadsheet. And I'm not that fond of either option, but I need to do one of them. So we are going to open up all of our constraints, and we're going to take a look at which of these. Oh, I've messed up my windows again. We're going to take a look at which of these refer to consequences.shelfAngle, because we have an alternate formula for that. We can copy this formula itself and edit this formula. Let's it's not actually that one. Here. So we replace it, we remove the equal sign, and we see that we are also using it here. We can also see that it's not actually exactly 8.4 degrees, it's 8.40333. One of those numbers we don't want to bother with because computers are good at that sort of thing. I am not. There. With those two constraints changed, and again we can give them more helpful names if we want to, but I have chosen to mostly set names for constraints that I am exporting. This spreadsheet should now be able to refer to sketch 001 or shelf size sketch, as I have also named it. And it contains constraints for shelf height and container depth. This is container depth. Let's widen that a bit, and we also collect shelf height here. Again, I'm going to copy it, I'm going to set the alias, and I'm going to enter the formula as that constraint. So, our dependency tree here, we have things from parameters going into shelf angle solver, and then the angle is going into the shelf size sketch, and data from the shelf size sketch and shelf angle solver both go into the consequences spreadsheet. We are going to maintain this dependency order, so for sketches that I am going to use, and we can see that these two sketches are, well, they're actually in the wrong axis because the z-axis should be pointing up, doesn't matter. But these two sketches are used to calculate all of the proportions. The next step is that we will redraw the shapes that are in this sketch in another sketch that will only depend on parameters and consequences. That way it's a little bit easier, I think, if I need to change any of these parameters at some point. I'm also going to use the part workbench to create the array of shelves and so on, so that's a later step. But at this point we have a fully constrained shelf size sketch. We have our parameters, they are calculated without any loops, so we can refer to the shelf size sketch inside of the consequences spreadsheet. And I think this is a good place to take a break. Thank you.